Use the power of imagination to explore thought experiments. Thought experiments enable us to sequence cause and effect to investigate consequences. Today, we will perform 2 thought experiments and learn how to detect analytics misbehavior. Often there is a tendency to rush ahead and focus on collecting large amounts of data while skipping past the obligation of considering the underlying context and logic we should implement to data mine actionable insights. Is the dashboard context valid? Is the underlying logic valid? If the underlying logic is not valid, then any consideration of dashboard accuracy is irrelevant. When we use a familiar analog to explore unfamiliar topics, we can instantly derive valuable insights. The light bulb in our head shines brightly, and we say to ourselves, "I got it. I now understand how it works." For our first thought experiment, let's build an online virtual bank to use as an example. You can open a free account with me today. To get a free account, just direct deposit your paycheck into the virtual bank. From this point forward, your current balance is calculated and displayed on your personal dashboard. The dashboard is updated each morning at 6 a.m. local time. The calculation is simple and very accurate. Current balance equals previous balance plus previous day credits minus previous day debits minus overdraft fees. Your account can be free because after we calculate your current balance each morning, we discard all of the individual transactions. This saves us space in our database, so we do not need many servers. After all, if the calculation is valid and executed each morning, what more do you need? We remove the tedious transactions so you do not have to deal with them. It is a win-win relationship. If your balance is low, simply deposit more money. Otherwise, no worries. What did you say? Oh, why are there overdraft fees if the account is free? The overdraft fees provide a convenient way for the virtual bank to provide you an instant loan whenever your account falls below zero. Your personal account is free, but the convenient overdraft loans are a billable service. Will you open an account with me today? We can create a network of machines. The machines talk to each other with signaling protocols to set up services, sustain services, and disconnect services to restore resources back to all resource pools. Each machine logs activity to periodic files called sample periods or transaction logs, which are generated every 5, 10, 15, 30, or 60 minutes. The network machine log files are designed by the network equipment vendor. Log files contain information as dimensions and measurements reported by counters. Capacity counters report the number of services delivered and the number of resources utilized. We use capacity counters to determine how much capacity has been consumed during the busiest hour of each day, when hourly aggregation is the capacity bottleneck announced by the network equipment vendor. We can then determine if we have sufficient capacity or if we need to add more capacity. Network machine counters announce values and are organized into a logical counter model. The logical counter model consists of dimensions of time and physical hierarchy associated to measurements of the various measurement groups announced by counters. The dimension of time has a hierarchy with the lowest level as sample periods, which then roll up into hourly, daily, weekly, monthly, and even yearly aggregations. The physical hierarchy has top level as the network with underlying levels of node, followed by card or blade, followed by connections, peers, or destinations. The logical counter model enables us to create aggregations to observe capacity bottlenecks at various layers so we can monitor and respond to capacity bottlenecks that get into trouble. The logical counter model evolves as the network and its supporting technologies evolve over time. As we transition into virtualization, we will see legacy counters associated to an individual specialized bare metal layer provided by a single network equipment vendor split into two new layers provided by two separate vendors. The two new layers are virtual machines or software and compute resources or hardware. This split of bare metal into two new layers creates additional new dimensions that must be managed. The logical counter model of the network machines are collected, parsed, and stored in analytics database format as tables with rows and columns. Sample period timestamps populate a vertical column of rows. Dimension and measurement names occupy columns. Their values populate rows within each column. It is not good enough for every cell of the analytics database to be populated. The information populated in the cells must be analytics ready. One common issue that can cause information in the analytics database to not be analytics ready is the challenge of poor naming conventions for nodes, connections, peers, destinations, etc. Another challenge is missing sample periods, causing the analytics database not to be 100% analytics ready. We are not talking about missing sample periods caused by nodes taken out of service for maintenance. Instead, we are talking about active nodes that carry traffic and their measurements are missing for some sample periods. This has happened when reporting processes within active nodes have unexpectedly stopped, gone to sleep, or have been disrupted. We are obligated to routinely verify the analytics database is analytics ready. We do this by creating extra dashboards to constantly report data integrity. For example, the extra dashboards reporting data integrity can count sample periods per day and sample periods per hour to flag days and hours having incomplete data. Also keep in mind there are two types of sample period information found in analytics databases. One type is the preferred unaggregated sample period information explicitly written by the network machines. The other type of sample period information found in analytics databases is aggregated sample periods, such as card level counters aggregated to node level totals at sample period time dimension. Aggregated sample periods can introduce other challenges. We can tie together everything we have learned so far and take a deeper dive by performing a second thought experiment. When we are learning something new, we can enhance learning and make it more personal by using an analog from everyday life. We use something that is very familiar to illuminate a topic that is less familiar. Let's take a road trip through the logical counter model, sample periods, and hourly aggregations. We are now observing from above a very familiar network we use every day, the transportation network. In this network, the network machines are cars, trucks, buses, and motorcycles. Each of these machines report the work they are doing via two special counters. They are the odometer and the speedometer. The odometer logs the miles traveled. The speedometer logs the speed moment by moment as we travel down the road. In this thought experiment, imagine that you ask a friend to take a ride with you as your assistant. Ask your friend to record some sample periods. You instruct your friend to reset the odometer to 0, then each 15 minutes record the current miles and speed in a notebook, then reset the odometer back to 0. Your assistant will do this until 4 sample periods are collected into the notebook. Once we have 4 sample periods collected, we now ask our assistant to create an hourly summary dashboard of the 4 sample periods. Our assistant does the math and creates the summary dashboard and announces that clearly we have traveled a total of 52 miles and had total speed of 216 miles per hour. What? This is a common hourly aggregation mistake. It's caused by not recognizing that the odometer and the speedometer are 2 different counter categories. The odometer is a peg counter and the speedometer is a gauge counter. When we roll up sample periods across the time dimension into hourly aggregation, we are obligated to apply sum to peg counters and apply average or max to gauge counters. If we apply sum to gauge counters, we cause a context violation. Saying we had an hourly total of 216 miles per hour does not make sense, especially when the odometer announced we traveled a total of 52 miles during the hour. Analytics tools will provide a list of functions such as a list of sum, max, average, and min, but that does not mean we are free to use any function anytime we want. We must select a function that does not create a context violation. Analytics tools do not prevent us from creating context violations. The analytics tool user is obligated to command, control, and communicate context. Sharing dashboard values without sufficient context erodes cross-team collaboration and spreads confusion. Each dashboard should exist within a context framework that enables some degree of independent verification and confirmation. The assertions of the dashboard should be traceable back to the source information. Dashboards having insufficient context is about as useful as a collection of random numbers and causes the dashboard audience to fill in the gaps with their own context and assumptions. How can we independently verify dashboards? To independently verify dashboards, we must have access to the source data that was used to create the dashboard. We compare the dashboard assertions and conclusions to the original source data. If the source data has been loaded into the analytics database in raw format, we can use the analytics database for the dashboard comparison. However, in some scenarios, we may have to trace back all of the way to the original machine sample period data that was generated and donated by a network machine. Some workflows require sharing examples of machine sample period format. For example, if new counters are added to the network machine, then machine sample period files generated by the network machine are attached to intakes that request adding the new counters to the analytics database. Software upgrades can cause existing network machines to add new counters. Machine sample period files can have variations of format. The most basic machine sample period format is to write network machine counters in 3 columns, as column 1 having the timestamps of a sample period, column 2 having measurement group and counter name, and finally column 3 having the counter values. A dimension-like node name may not appear within the machine sample period file because it is found in the machine sample period file name. The analytics database collects and parses machine sample period files at specified time intervals, then stores the collected information in the analytics database. Once the machine sample period information is stored in the analytics database, it is possible to create and publish automated dashboards that are continuously refreshed to provide up-to-date insights. Even though we automate useful dashboards to provide periodic insights, there will be times that they will produce suspicious assertions and conclusions. When this happens, we may need to trace the dashboard source data all the way back to the machine sample period file information. One such scenario would be missing sample periods. If we observe certain sample periods missing from the analytics database, we would compare the analytics database to the original machine sample period file information to determine if the missing sample periods are also missing in the network machine. If the missing sample periods are missing in the network machine, then the network equipment vendor may have to be engaged to resolve the issue with a software fix. But if the missing sample periods are not missing from the network machine, then it can be an indication of analytics database parser misbehavior or malformed machine sample period file written by the network machine. I have seen other issues, such as counter values having blanks or false zeros within the machine sample period file. This type of issue was resolved by the network equipment vendor providing a software fix. It is important to always remember that the information we see in the analytics database is only a representation that is asserted to be donated by the machine sample period files. Due to misbehavior that can happen within the network machine or analytics database, they may disagree and contradict from time to time. There is no guarantee that the information in the analytics database is truly representative of the information donated by the network machines. We are obligated to do the work to compare analytics database information to machine sample period file information to resolve certain types of issues. In fact, we have no guarantee that the information in the analytics database aligns with the information in the network machines, because network sample period files are collected and parsed only with best effort intentions, without any checksum comparisons to concretely confirm data integrity as information is loaded. Therefore, the analytics database user will sometimes require access to machine sample period file information to verify data integrity when the dashboards misbehave. Think about the online virtual bank thought experiment we explored at the beginning of this video. When the virtual bank dashboard involved our own money, we did not like being forced to rely only on a simple dashboard summary to announce our current balance. Not having access to all individual transactions so we could confirm dashboard summary assertions raised loud alarm bells in our head. We should have the same discomfort in scenarios in which we have dashboards announcing suspicious displays that cannot be independently verified or traced back to information donated by the original network machines. The analytics database dashboard creator has explicit obligations that should not be overlooked. Data integrity verification obligations. Does the information in the analytics database accurately reflect the information donated by the network machines? We can create extra dashboards to measure and flag data integrity violations. Count and report the number of sample periods per day and per hour. This will expose when sample periods are missing, which then enables us to flag and alert when capacity dashboards are working with incomplete source information. Missing sample periods will cause peg counter hourly aggregations to be underrepresented. Missing sample periods will cause gauge counter hourly aggregations of average values to be underrepresented and can cause max values to be missing true max of each hour. Count and report the number of contributing nodes per day and per hour. Missing nodes can indicate nodes were taken out of service for maintenance, or can also represent active nodes that provided services but failed to report within the machine sample period files. Active nodes that fail to report activity in machine sample period files will cause network total dashboards to underrepresent true network total traffic. It appears as a drop in network utilization that did not actually happen. If any node information is missing from a network total dashboard and the network total traffic appears to be reasonable, then the missing node was likely taken out of service for maintenance or had an outage. Therefore, when network total dashboard reports unexpectedly drop in network utilization, check for missing nodes, missing sample periods, or other missing contributors. Does the dashboard hourly aggregation contain any context violations? To verify if context violations exist in dashboard hourly aggregation, go through the manual steps of collecting the source sample period data, then create your own hourly aggregation to see how it compares. Do peg counters in hourly aggregation use sum to calculate hourly peg values? Do gauge counters in hourly aggregation use max or average to calculate hourly gauge values? My security badge is like many security badges. It has a picture with my name on it on one side, and it is blank on the other side. Sometimes, as I am walking down the halls, my badge flips around so that only the blank side is visible. When this happened, the badge seemed to be useless, so I thought I would fix the problem. On the blank side of the badge, I drew an emoji with the generic emotion I have most of the time. Next, I labeled it to be me. From my perspective, this display is 100% accurate. It correctly announces that I am me, so the security guards do not have to worry when they see me. In reality, I did not fix the problem of the badge flipping over to the blank side. I created an unverifiable assertion. Why is this a problem? It makes assertions and conclusions that cannot be independently verified or confirmed. This security badge display is completely useless. Unfortunately, analytics dashboards can be just as useless. I have seen network dashboards that made it appear that a network outage had occurred when no such outage happened. Instead, the dashboard was corrupt. I have seen dashboards missing vital context, which then causes the audience to fill in with context of their choice. This type of dashboard communicates misinformation as it is misinterpreted by most viewers. I have found dashboards polluted with context violations, communicating nonsense. Fixing these issues can require rehabilitating the dashboards, the underlying analytics database, or even the source machine sample period information. Finding and fixing these issues requires the heavy lifting of investigative manual intervention if steps are not taken to proactively and routinely verify and confirm data integrity as dashboards are refreshed.